how to use the mechanical structures sort of to increase the sensitivity, right? To increase the sensitivity. Okay, yeah, that's very important. That's very important. And then in this case, mechanics can also play a very important role. But then the people come up with some bio-inspired approach, right? For instance, in the case of spiders, okay, they're so sensitive. The spider lives based on sensing of vibrations. Okay, if there's a prey, right, in the net, they will cause tiny vibrations. Then they can sense. Okay, so how can they be so sensitive? So in this case, people look into the feet of the spiders. They'll find out that there are tiny cracks. Okay, there are arrays of cracks. Okay, so what does this crack do? Well, without going into details, so the crack actually make the sensing much more sensitive. It's kind of localize the strain, and then reduce the overall stiffness of the tiny feet, and then so this way, when there's a deformation comes, and then the resistance change can be much larger. Okay, so yeah, if you speak in terms of the gauge factor, that can be very large, like can be thousands. For a typical material, maybe only a few. Okay, so mechanical design in this case plays the key role, right? Actually, a lot of examples from the natures. In this case, they are strategically using the cracks, right? Take advantage of the cracks.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwiney, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. Maybe firstly, I would like to ask you how you would like to define yourself. Will be people first time listening to you. How would like to define yourself?
Well, okay. I'm a professor at NC State University. I teach in mechanics materials and micro and nano systems, and so that's my teaching area. So my research areas in anywhere from mechanics to these days to soft electronics, soft robotics using nanomaterials. I think that's about me.
Yeah, great. So maybe before going to your research, especially in soft robotics, and I think you have really a great research line here, but maybe I'll ask you what maybe challenging so far you can highlight the challenging aspect in soft robotics from a material perspective, and also the mechanics, if you can tell us maybe something interesting about mechanics and structure. If you can tell us what are the challenging aspect as a general view for soft robotics.
Okay, yeah, that's a great question. For soft robotics, as you see, it's multidisciplinary. Materials definitely plays a key role, right? Mechanics and design also plays an important role. So in terms of the materials challenges, I would say, so for soft robotics, right? So you see, it includes several aspects, right? We are talking about actuation, right? We're talking about sensing, and also have electronics. Okay, so this is three sort of components for soft electronics. For each of them, we would require novel materials. Okay, so as an example, let's say for the actuation purpose, right? We want materials that, first of all, that is soft, and then depending on the actuation mechanism. For instance, if you involve thermal actuations, then you want to have a soft materials with a high thermal conductivity, which itself is a challenge, right? And then Also, we want the materials to be responding quickly. Okay, so also oftentimes we will have materials that can be quick and also reversible switching between a stiff state and a soft state. Okay, and also we want materials that can have a self-healing capabilities, right? And also materials that are stretchable. So this really a wide range of requirements for materials, right? Because as we know, right, software electronics and software robotics, right, there are sort of emerging field, right? So posting very different requirements in terms of materials. So they are very different from the materials that are used for the rigid robotics, right? So well, that was a general answer. I hope, but I would say in general, we would need to have materials with very unusual properties, very unusual combinations. Okay? And you also were asking about mechanics and design. Also plays a very important role. Okay, because robotics, at the end of the day, is a mechanical device, right? So how to optimize the structure, right? How to optimize the architecture of the robotics, that also plays a very important role.
It's very interesting. Maybe I want to ask you, because you mentioned that very interesting point about the design and the trade-offs. Maybe when you try to look to the design that we want, for example, stretchable material, and we have this conductivity, there is many aspects here. What do you think may be the lacking point here? Do you think it's modeling? Do you think it's material properties? Do you think understanding mechanics? What is missing here to achieve what you mentioned? Do you think this is the aspect here missing?
I think all the aspects are important, right? Because the software robotics is truly multidisciplinary. But I would put a little more emphasis on the materials aspect, because the materials is, at the end of the day, is something really that makes things happen. As I briefly mentioned earlier, right? So the materials requires unusual combination, right? You also mentioned. So you want something to be very soft, but also to be electrically conductive, right? That's challenging. Or thermally conductive, that is challenging, right? So many people, many groups are working in the area. Let's say, especially for soft electronics, I would say the materials development for soft electronics has been going on for quite a long time, maybe 1 decade, maybe 2 decades now, right? So a lot of new materials have been developed for soft electronics, or let's say maybe stretchable electronics, right? To be more specific, right? Which is quite challenging. So we have different types of materials, right? Which can be stretchable, but right, you can have microfabricated materials, right? Thin films, but you can use some mechanical design to make them into some stretchable configurations, right? Also, you can use nanomaterials, right? You have 2D materials like a graphene, you have carbon nanotubes, you have nanowires, even nanoparticles, right? You can put them in a composite form, okay? And also maybe with some mechanics design guidelines, okay? Then you can also make them stretchable, okay? Also polymers, right? You can have conductive polymers, right? And so all these are materials, okay? So they have been used for soft electronics. I would say a lot of these materials can be used for soft robotics, and also a lot of there's some design guideline, right? Especially some mechanics principles behind this to make them stretchable. So all those can be used for soft robotics. Okay. I hope I answered your question, right? So in general, right, multidisciplinary and materials very important, but mechanics and also useful.
Yeah, I think that's interesting. Maybe I want to highlight the example here. But I think the question I'm really curious about. You mentioned that we need more emphasis in material aspect. But I was about to ask you which more significant maybe part you think may be interesting for designing soft robots or machines. Is it the material part or architecture structure? And why I'm asking this question, for example, when we look at the toughness, how we can increase toughness in soft structures or soft material, there's intrinsic way and extrinsic way to increase the toughness. And when we look to the intrinsic one, maybe the material part, and the extrinsic ways to increase toughness in softer material,
it get more interesting, and there's rich mechanics maybe behind it, how the morphology or geometry of the soft material, different soft material, can increase toughness. That's why I'm asking you, where do you think maybe the right approach is? It intrinsically in the material, embedded in material level, or just playing in the mechanics in the continuum level of the material?
Okay, yeah, very, very good question. Very good question. Yeah, I think my short answer is we need it from both sides. Okay, we need it from both sides. But the mechanics principle has been in place. Okay, so the mechanical design, right? We know how to for instance, to minimize the stress. Okay, and then we know how to, for instance, you talk about fracture toughness, right? We know how to design properly, right? Say, so to minimize the stress, so that it's suppose you have an existing crack, the crack will not advance, right? From the mechanics point of view, we can reduce the stress, but from the materials point of view, we can increase the fracture toughness. Okay, the material itself can increase toughness, but the mechanical design, right? Also the structure, the overall structure design can have a way to reduce the stress. So for a crack to advance, right? But let's just be specific with the crack as an example, right? For crack to advance, you really need to have the loading, right? The external loading, which comes with the stress. And so you need to make sure that loading, the stress state, is not. Well, from there, the loading, you're going to have something called a driving force. Okay, but make sure that is less than the intrinsic toughness of the material. So it's like the two sides of the equations. Two sides of the equations. So we need both. We need both. But the mechanics principles are, I would say, are mostly established. Well, mostly established for stiff materials, but with some extensions. Okay, so I think that to the new materials, to the new softer materials. But I would say in general, the kind of established. But more innovations are still in materials aspect, because again, softer materials is in general a new class of materials, right? And then especially in this case for softer robotics applications, we're talking about soft and functional materials. Okay, so when you introduce this functional element, then they will also introduce some additional limitations in terms of, for instance, you may not be able to get the toughest, the soft material, because you want to make that material also functionally, right, electrically conductive. Then you have to, following the composite approach, you have to introduce some other phases, right, nano fillers, for instance. Then that could also affect the mechanical properties. But yeah, I think both are important, but I would say the materials could have a wider space in terms of innovation, because just mechanics is it's elegant, but it's a bit more established.
That's interesting. That's an interesting answer. Maybe I want to ask you in that regard, because you really highlighted the answer in a very beautiful way. Maybe I want to ask you maybe what's still maybe lacking or missing in understanding. Since you mentioned mechanics is established, do you think there's other ways to understand the structure to give us interesting behavior in the mechanics level, just not material level? Do you think there's other missing approaches or studies to understand what's actually happening in the continuum level to increase certain functionality? Do you think it's very established, or still do you think there's missing aspects here?
Okay, yeah, good question. Because when we say mechanics, we typically say mechanics of materials. So as you can tell, so mechanics always goes with materials, right? For instance, when we look at the bridge, right? When we design a bridge, okay, we need to make sure the bridge can take how much force, right? But at the same time, we need to make sure the material selection, right, based on that predicted force or stress level, right? And then you choose appropriate materials. Right? So it's really both are they go hand by hand, right? You never be able to separate the two. When I say mechanics is more established, it's more of the mechanics principles. Okay, the principles are more established. For instance, they're based on let's say Newton's law, right? It's still Newton's law. It works for not only stiff material, it also works for softer materials, right? So we have a lot of the equations right? In mechanics, right? We talk about the stress distribution. All this, the principle, the mechanics framework, it's elegant, right? It's very beautiful. But all those are established. But there will be some modifications, right? When you introduce some new materials, for instance, right? For rigid materials, we oftentimes use a small string called assumption, okay? Because we assume is a linear elastic deformation, right? But for soft materials, then we cannot do that. We cannot do that, right? Because the large deformation is involved, and then the mechanics becomes more complicated. Okay, more complicated, but it's still established. Yeah. The framework was established. That's what I mean. But I'm not saying mechanics is not important. Actually, my field is mechanics, so I just cannot emphasize enough the importance of mechanics. Okay, so for all these designs, right, for structural purposes, in this case, soft robotics, right, so you have the functional materials. As long as there's deformation, there is movement involved. Mechanics is critical. So we must understand the basic mechanics principles in order for any of this to happen, right? So for soft robotics, I said, well, we can develop some new materials and all this, right? So this can make software, but this will not go without the basic mechanics understanding.
That's very interesting. Maybe I'll go, because also in the sensor, soft sensor, maybe you mentioned at the beginning this kind of a trade-off. You need stretchable, for example, and you make sure this conductivity is there. And it seems there's a trade-off how to, if you want, for example, let's take example, designing sensor, multimodality sensor, and you need to measure different signals, and it seems that there's a consideration for the morphology or the geometry and also material properties. Can you tell us more from your experience this kind of trade-off if you try to design sensor, multimodality sensor, or just one sensor, for example, strain? You can make an example you think may be relevant here, but how do you see the combination of the morphology, shape, with material properties to design sensor for a specific signal and make sure you get the right thing? You're measuring strain, you're not measuring any other signal. You see what I mean?
Yeah. Okay, yeah. Very important questions, because we are talking a lot about soft sensors, right? But oftentimes, you want the soft sensors to measure something, but oftentimes you may measure other things, also other signals. Okay, so exactly to your point, right? So how do you isolate? Right, there's no so-called crosstalk, right? No crosstalk between the signals. Right? I can take maybe one example is temperature sensor. Okay, temperature sensor. We a couple of years ago we developed a stretchable temperature sensor. Okay, and then that can be placed on the skin. Right, it's important to measure the skin temperature, right? Which is a vital sign. Right, so that's very important. So there's different mechanisms to measure temperature. The way we choose is essentially the resistance change according to the temperature. Right, so it's a resistive mechanism. But the problem is there's many other inputs that can change the resistance. For instance, the stress, okay, or pressure, right? So we are talking about the application for wearable temperature sensors, right? When you wear it on the skin, right? So first of all, to put on the skin, you will introduce a little bit deformation, and then that can change the resistance. And then also during the motion, right? And then so your skin may deform and so on. So that can also, you see, the mechanical deformation can change the resistance. So how can you decouple these two? How can you decouple these two, right? So in this case, no matter how great the material is, you cannot solve the problem alone, because let's say the material is so sensitive to temperature. But then it still doesn't solve the problem. So in this case, we resort to a mechanics design. Okay, so specifically we use the so-called kirigami structure. Okay, so the kirigami structures, right? I think many of you might know. So essentially, it's a Japanese art. It's a cut. Okay, you can cut many. You can have a distribution of cuts. Okay, so when you cut those, and then when you stretch it again, what happens is then you will have the ligaments, connected ligaments. When you stretch it, the ligaments connected between the cracks, they will rotate out of plane. Okay? So as a way to effectively reduce the stress. So even though the entire structure will change the stretch by 100%, but the local strain is very, very small. It's less than 1%. So the local strain is what matters, is what changes the resistance. Right? So in this way, we effectively, even though you have deformation, but the strain-induced resistance is minimized. Then what you measure is only from the temperature. The resistance changes only from the temperature. Okay, so here I'm just taking this as one example, right? So how to avoid the strain, right? When you measure temperature. So many other cases, right? So you have, because you can measure many different signals, right? For instance, we are talking about electrodes. People are using the electrode, okay? The electrophysiological electrodes, okay? That's also a common soft electronic devices, right? There you also have so-called motion artifacts. Okay, so when it moves, actually, it will cause mechanical deformation. It will cause a sliding on your skin, and it causes mechanical deformation. Right? So those, yeah, you also need to address those. So it's for all this consideration, mechanics or design plays a key role.
That's very interesting. Maybe I want to ask you in this regard about sensitivity in design. You mentioned decoupling, mechanical deformation, and I think that's highlight the mechanical design. But I want to ask you in this regard about increasing sensitivity through structure. Do you think, how do you think about this part, not only the material, but also structure, to increase sensitivity? Do you think what we may be lacking here or missing here to get the advantage of the structure of the sensor, or, yeah, soft sensor here, the structure?
Yeah, okay. Okay, I think in the previous example, in that example, we try to get the intrinsic measurement of one signal, right, and then try to mitigate the effect from another signal, right? I think this question, you say how to use the mechanical structures sort of to increase the sensitivity, right? To increase the sensitivity. Okay, yeah, that's very important. That's very important. And then in this case, mechanics can also play a very important role. Actually, maybe let me give you an example of maybe a strain sensor in this case. Okay, strain sensor, what happens typically when you strain something, let's say we use a resistor. There are different strain sensing mechanism, right? It could be the resistance mechanism, resistance change. It could be capacitance change, right? Let's take the resistance mechanism. That's the simplest strain sensor. So what happens is when you stretch it, okay, and then the resistance will change. Either the resistivity will change or the geometry changes will cause the resistance change, right? But then the people come up with some bio-inspired approach, right? For instance, in the case of spiders, okay, they're so sensitive. The spider lives based on sensing of vibrations. Okay, if there's a prey, right, in the net, they will cause tiny vibrations. Then they can sense. Okay, so how can they be so sensitive? So in this case, people look into the feet of the spiders. They'll find out that there are tiny cracks. Okay, there are arrays of cracks. Okay, so what does this crack do? Well, without going into the details, so the crack actually make the sensing much more sensitive. It's kind of localize the strain, and then reduce the overall stiffness of the tiny feet, and then so this way, when there's a deformation comes, and then the resistance change can be much larger. Okay, so yeah, well, if you speak in terms of the gauge factor, that can be very large, like can be thousands. For a typical material, maybe only a few. Okay, so mechanical design in this case plays the key role, right? Actually, a lot of examples from the natures. In this case, they are strategically using the cracks, right? Take advantage of the cracks.
That's really wonderful. First of all, I'm very passionate about spider, and I'm so glad you mentioned that, because I wasn't aware about the crack. I think that's a very interesting topic, but yeah, I'm very glad you mentioned the spider example, because it's very, yeah, I think it's something we discussed somehow in the podcast, but not exactly as one of the crack. Maybe if you can elaborate more Because I think what you mentioned about the spider leg is very also related to designing soft material, maybe to resist damage or something in this nature. Maybe when you mention high gauge ratio, you mean the change in resistance will be more significant than the strain, right? Just elaborate. Is that what you mean by high gauge factor here?
Right. With the crack, with the crack, the resistance change will be much more than the case without crack.
Very fascinating. Yeah. So maybe I want to ask you, in the paper you also published in Soft Robotics about how you can increase the temperature, maybe thermal conductivity or the stimulus for actuator. And if you can explain the concept behind using two different materials to thermal expansion, it's really interesting that you take advantage that this kind of non-similar thermal expansion for the material to form bending actuation. Maybe can you tell us the story behind this paper?
Sure. Absolutely, yeah. So this actuation principle is called a biomorph, okay? Particularly called a thermal biomorph structures. So exactly as you said, you bond the two materials together, okay, with different thermal expansion coefficients. And then you heat them up. When you heat them up, what happens is, well, one material expands more, the other expands less, right? But they are bonded together. So what happens? So as a result of the mechanical interactions, well, the two will interact, negotiate between each other. As a result, they will bend. Okay, the bilayer will bend. Okay, so the outer layer has a larger thermal expansion coefficient. The inner layer, okay, has a smaller thermal expansion coefficient. So what happens is, well, the thermal expansion, okay, the axial deformation is very small. But now with this bending, okay, it's really amplified the deformation. The bending deformation can be much larger than the axial deformation you get from the thermal expansion of a single material. Okay, so that's the basic principle of this thermal biomorph structure. And then, but in this case, we have a larger deformation here, right? Because we are using this for soft robotics application. So the strain is quite large. It's much larger than the typical rigid materials. Okay? Rigid material also use this biomorph idea, but the deformation here we are having is much larger. And then the challenge is, how are you going to heat this up? Right? We have an embedded heater. Okay? We have an embedded heater. The heater is between the two layers in between. Okay? And then we run current through, so we're using the Joule heating, right? So we can heat up the structure. So then the heater is also being deformed, right? It's also being bent. Actually, the heater, because of the entire thing, has a very large deformation, right? So the heater is also being deformed, right? And then it will require a deformable heater. Right? That can be a challenge. Oftentimes, when you deform a heater, well, maybe the heater will fail. If it doesn't fail, the heating performance will change. It's because of the resistance changes. Okay, because this is Joule heating, right? So the resistance changes, then the heat generated will be changed, right? So in this case, this work is built on our previous work based on stretchable conductors, where the resistance doesn't change or change very little. Okay, even under stretching. So in this case, we have deformation. Well, actually, some stretching in the heater, but the resistance doesn't change, so the heating performance remains constant.
Interesting.
Yeah.
Maybe I want to ask you if there's maybe disagreement in the way of the design when it comes to this. Is one of the example to avoid this problem. But do you have any example you can recall that you can maybe highlight if you have disagreement or different views or approach to design in soft robotics? Do you have different view or disagreement when it comes to soft actuator design, or certain example you have different views on?
Okay. Maybe I will tell a little more about this thermal actuator I was talking about, right? The thermal actuator, so this is thermal biomorph, right? It's nice. It can bend quite a bit and so on. So in general, in the field of soft robotics, there are different actuation methods, right? It could be a pneumatic pressure, it could be heat, it could be electric field, it could be a magnetic field, or even chemical potential. So people literally have a combustion engine inside the soft robot to power this. But the problem is no actuation method has yet emerged as the dominant one, because every method has pros and cons in terms of the force, the speed, and then also requirement of auxiliary equipment. For instance, in the case of pneumatical pressure, right, you have to carry a pump with you, right? So thermal actuation also, right? Thermal actuation is nice because it's based on the joule heating, right? So it can be programmed, right? The device is lightweight, low actuation voltage, and then you can have potential for untested operation because you can have a wireless charging, or you can use light. The light can be turned into a heat, right? If you have a heat absorbing material, right? But the problem is relatively slow. Okay, so this you're asking for the disagreement, or you see people. We have interest in the thermal actuation, right? Because it's so great. But now the major challenge is slow. This is an inherent challenge because for soft materials, the thermal conductivity is low. Okay, so that's the nature of soft materials, because they're polymers. Okay, they are not like a crystalline material, like a metals or ceramics, right? Can be very fast in conducting heat. So it's slow. Okay, then people say, okay, the idea we can dope some nanomaterials inside to increase the thermal conductivity. Yes, that's a natural idea, right? We did that. It did improve to some extent, but not much, because you cannot put too much of this nanomaterials. Okay, if you put too much, it will tend to agglomerate, causing other issues. Okay. And then, so how do we address this problem? So that's exactly what we reported in the paper. So one day we look at this Venus flytrap. Okay, the Venus flytrap that's in the nature, right? So there's no much, well, there's no much a faster actuation mechanism, something like a electrostatic actuation. Right? They don't have that luxury, right? All they have is there's some water. Okay, there's some water. Anyway, in the nature, right? So the budget is very limited, right, in terms of resources and so on. But also, why they can still deform very quickly, because they have to catch the prey, right? It's the Venus flytrap. So what happens there? They actually take advantage of this called the mechanical bistability. So initially, the Venus flytrap, or the one lobe, right, or two lobes, right? If you look at the one lobe, it's essentially a film, but it's a bent in one direction. The film is bent in one direction. Okay, and then upon actuation, what happens is you will quickly bend into the other direction, right? Suppose the film, you will have two directions, right? In plane, you have two directions, right? You have two directions. So initially bent in one direction, but then it quickly switch to bending in the other direction. So that mechanical, called a snap through, that happens very quickly. The switching happens very quickly. Oh, we thought maybe we can introduce this into our thermal actuators, right? So if we can introduce this kind of snap through, and then the actuation speed can be very fast. So that's what we did. So yeah, we introduced a little bit of pre-deformation. Okay? We introduced a little pre-deformation, and then when we hit it, and then up to a critical point, you will suddenly switch to another state. So that snap through is very fast. So that's what we did. So it's really bio-inspired, and there's a lot to learn from the nature. I think especially in the field of soft robotics, right? Because everything is soft. The nature is soft, right? The human beings, right? All these are soft. So there's a lot we can learn. A lot already has been learned, and this just another example. The mechanical instability can be very nicely done in the nature. Also can be learned.
Wonderful, wonderful. Maybe I want to ask you if there is any example, maybe in mechanics of material, not explicable or very challenging to explain. Do you have any encounter, like, if you can recall this kind of explaining the behavior of the material or certain design that the mechanics was quite challenging to approximate why this happening? Do you have this encounter, like counterintuitive or I don't want to say inexplicable, but it's maybe hard to explain in mechanics alone.
Okay, very good question. Okay, I need to think. Because in general, mechanics of materials, right? It follows the very, very basic physics laws, right? So I would say everything, as long as it involves structures, as long as it involves deformations, okay, they are operated following mechanics principles. So, well, people can have different understanding of mechanics, right? Or some people may misunderstand some of the mechanics principles, right? But I would be surprised if the mechanics and materials principle cannot be used to explain some phenomenon, because well, maybe one example. I'm not sure if it's totally a good one, but for instance, we're talking about so-called size effects, okay, and then the mechanics laws are still prevalent, but the behavior, the material behavior, could be different, right? So, for instance, when we look at, I deal a lot with nanomaterials. Okay, so we are interested in mechanical properties of nanomaterial. For instance, nanowires, right? Tens of nanometer in diameter. So what happens is that the surface of the nanowires, their mechanical property can be very different from the inside of the nanowires. Why? It's because of the surface, right? So the nano, you have this surface layer. The surface, the atomic arrangement of the surface, is different from that of the interior. Right? So if we look at it, maybe not nano, just look at the surface of anything, any structure, small or large scale. Right? So how to create a surface? To create a surface, you have to cut the neighboring atoms. You have to cut the other half, right, in order to create this surface. So what happens to the atoms on the surface? Right? They all of a sudden lose all the neighbors on the other side. Okay? And then what happens to them? They will have to adjust, because when they lose the neighbor, for each atom, they have to follow the mechanics law. They have to keep the balance, the force balance for each atom. Right? Now they suddenly lose the neighbor, so that means they lose either attractive or compressive force, right, from the neighbors. They have to adjust themselves in order to be balanced, right? The equilibrium conditions, works no matter what scale. So they have to readjust the configuration. They will probably be pulled in a little closer to the interior atoms, right, or the neighboring atoms on this side. Okay. So anyway, they will have to, it's called the self equilibrium. They have to adjust to this. Okay. And then, so as a result of this reconfiguration, so let's say the bonding length can be very different now. Okay, the bonding length can be very different from those atoms in the interior. So there they will have the lattice constants, right? But for those layers on the surface, or it can affect a number of layers, okay, down into the bulk. So the properties can be very different, right? So then you have to take those into account, right? If you just take the bulk properties, right, so treat that for the surface, then you can lead to quite mistakes, okay? Or the approximation would not be reasonable. So I hope this example explains. My message is the mechanics of materials, the principle still works. Okay, the principle works across the scales. I don't know, maybe when the speed changes very high, when you go to the relativity theory, maybe there's something different. But otherwise, from typical applications, right, the mechanics of materials principle in the Newton's framework would still work. But we do need to look into the material systems, right? We do need to understand what kind of bondings are involved, right? What kind of interactions.
Very interesting. Maybe since the close end, a few questions left. Maybe I want to ask you about the material that can be used as both actuator and sensor. And I'm asking you this question. I had this maybe experience a couple of years. I was working in a conductive polymer, and I know that it has limitation. The force produced is so much high, and sometimes it's very slow response. And it seems that it's bring again the beginning what you mentioned about the wish list and the material that what you want. For you, when you try to think about material that has these all features, actuation, sensing, and the response time and the force, if you can pinpoint exactly now, maybe the right way to achieve this wish list in the material, what does it take to achieve this kind of wish lists and the design of the material like this?
Okay, I would say, well, for the wish list, I would have the materials, right, with all the properties we mentioned, right? Fast response, right? High electrical conductivity, thermal conductivity, self-healing, and you can change the states between being stiff and being soft and all those, right? So this would require a lot of development from the material science community, chemistry, physics, or material, also mechanical engineering or electrical engineering, right? But I think realistically speaking, you may not be able to get one material that fits all, right? So I think different materials. Then you will come to the material selections, right? We have to select for different applications. We have to select appropriate materials. Okay? It always go hand in hand. You select wisely, select the materials, and also you advance the materials, right? So I think both are important. Both are important. With this soft electronics, soft robotics, right? It definitely pose a demand, right, for new materials, right? So for instance, some of these composite ideas I mentioned, right? You can put ceramic particles in the matrix to enhance the thermal conductivity. You can put metallic nanowires in the matrix, right? Then you can have a soft conductor, right? That does not change resistance with the strain. So those are new development in response to the need of the field, and but then we can still strategically select these materials, right? And then also with the mechanical design, right? So mechanical design, for instance, well, even right, I think I also mentioned earlier, even for thin films, right? The materials are the same, but you can pattern them in certain ways, right? They call it like a serpentine patterns, right? So those ways to effectively reduce the stress, right? So they can also be stretchable. I would say, it's probably very difficult. It will be ideal, but it's very difficult to have a wish list for materials with all the properties. But I'm sure the materials field will keep advanced to meet fields. But at the same time, we can borrow some other concepts, right, from the design point of view, to try to reduce the demand for the tough, for the highest demand from the materials. My point is the materials are important, but alone might be difficult to solve a lot of these new challenges.
Maybe two questions. Maybe the first one about physical intelligence. I want to take your views about morphological intelligence or physical intelligence and how we can exhibit intelligence based on just, in passive material without any stimulus and still can give us intelligent behavior. Do you think, how do you think about morphological intelligence if we speak in passive material level? Do you think, what do you think about that?
Right. Okay. Yeah. Okay. Very good question. In my view, I think the physical intelligence is really coming from both ways. One is the material itself, and then in that sense will be the smart materials, right? Responsive materials, you can call it. And the other, I would say, physical also depending on the highly related to the data science, right? When you have a lot of data, and then you can extract information from the data, and then you can optimize information from the data. So I would say, to me, I have to say that I have limited experience with physical intelligence, But my view of this is from including both ways. From the materials aspect, right? Then you have to make the materials responsive, right? For instance, people develop the magnetically actuated robots, right? The robots are very small that can move around inside your blood vessels. So those are from the materials levels, okay? But in terms of the data science level, I would say is then you can have a large amount of data, right? And then using algorithms, right? You can use a deep neural network, all those things to optimize the behavior of the devices. So that's my take. I think that the both aspects are very important.
Maybe the one or two question now. I think what kind of feature, when you try to think about material in general, if you look to evolution, nature, they have this feature, or maybe something in your imagination that you wish this feature, functionality in the material, and still not touch it, maybe in discussion, scientific discussion. Do you have any kind of ideas like this feature, I wish this feature in the material?
Okay. Good questions. I think we talk a lot about the materials, but the materials is really endless demand for new materials, smart materials. I would say the nature provides endless inspirations, right? I think especially for the field of soft robotics, I think we need to look more into the nature. There are different kinds of materials in the nature, right? They live with very limited resources, okay, but they can perform the functions, right? They can perform the so, and that's I would say right. We look into not only maybe animals, we can also look into plants, right? So the animals, of course, right? Let's say if we look at the cheetah, right, that could provide a lot of inspirations for us fast-moving robots, right? But also for plants, the example I just gave, the Venus flytrap, right? That leaves also almost no resources. Actually, it's quite interesting. This Venus, the natural habitat of Venus flytrap. Well, the native here in North Carolina, okay, in a place close to the beach called Wilmington, okay, Wilmington Beach in North Carolina. So it's kind of native here. The reason you have this Venus flytrap is because of the soil is so poor that it doesn't provide enough nutrition. So they have to eat some extra to supplement the nutrition. Okay, so they have to capture some prey. You see, I just sometimes I feel amazed, right? The nature is just so smart. Okay, they can be self-adaptive, right? Like in this case, right? How does it know? Okay, well, I need to have some additional supplement in my diet, and then I develop this bistable mechanism, and then I use it to capture prey. It's amazing. It's amazing. Yeah. Well, a lot of the sea animals also they provide inspirations, right, for underwater robots, right? Even the fish, right? Just if you look at the fish, how the fish vibrates, right? Just basically bend the different parts of their body that creates the propulsion, right, to move them. Right? The fish swims basically like seamlessly, effortlessly, right? So it's quite amazing. Yeah, there's a lot to learn. So to answer your question, my wish list is I wish, or for different applications, right? For different applications, we can get the materials that can mimic the functions of the best living things, right? Be it animals or plants, in that category, right? If you want to have something fast as cheetah. If you want to have something swims without any effort, right? You look at a lot of these fishes or jellyfishes, right? That can hide themselves, right? It can be behind the rocks and so on. So all these features, right? The different in the living world. Yeah, I think those kind of provides the inspirations for the material scientists. If we can develop materials, of course, for different applications, right? We can learn from different living species.
That's very beautiful examples. Maybe the last question: what makes you fulfilled, and maybe the moment, that you feel that very satisfied with what you do?
I would say in two aspects. Well, but still, yeah, thank you for the question. Two aspects. One is for research. For research, oftentimes, we work with students, graduate students, postdocs, right? We work on some problems, maybe for weeks, for months, oftentimes, sometimes even in years, right? It doesn't really, the things doesn't work. We tried all this, it failed, and so. But all of a sudden, it worked. That the eureka moment. That really means the word to me. As a researcher. And then so that will make you all the efforts, right? All the day and night. You feel that's worth it. Because for researcher, you always want to do something new. Right? You also want to try something that people have not done, right? So as long as you push that envelope a little bit, right? As long as you make a little bit of new contributions, I think that makes me satisfied. The other one is from the teaching point of view, right? The teaching point of view, right? So for us, right, we not only research new knowledge, right? We also want to transfer the knowledge to the next generations, right? So we work with students in the lab or postdocs in the lab, right? So then the new skills, right? Then they becomes expert in their field, right? Then they move on, right? They move on to become professors, to become researchers, and so that is satisfying. And also even for the undergraduate students, right? When we teach the classes, when they come to the class, I teach mechanics of materials, in the undergraduate level, also graduate level. So when they come to the class, they have little knowledge, or even no knowledge about what stress is. They may know what force is. But they have no idea what stress is. They don't know the difference between stress and pressure. And but by the end of the semester, they know how to do some structural design based on the stress principle. They need to make sure when I design this, the maximum stress cannot exceed a certain limit, and so. So thus, it makes you feel, wow, this semester is really worth it, right? The students now, at least they are one step closer to being ready to go out to the world.
Mm-hmm. This is inspiring. I don't know if you have any final words you'd like to say.
Not really. All I would say is I think software robotics is a fantastic field. I have to say it's actually a relatively new field to my group. We have done quite some work in soft electronics, soft sensors, but so far we have found it's fascinating. We have found the materials we do, the soft material composites, and also mechanics plays a very important role, but also multidisciplinary. We do the electrical engineering, the heat transfer, all this plays an important role. So it's absolutely a fascinating field. It's interesting, and also I hope that it's relatively new. That many people can make contributions from different disciplines. As for in the nanotechnology field, right? We often say there's plenty of room at the bottom. I think for these soft materials, I would say something similar, right? There will be plenty of room to explore for this field.